Have you ever stopped to think about how our planet deals with the absolutely massive amount of energy the sun throws at it every single second? It's all a really delicate dance, a cosmic balancing act that's happening all the time across these invisible layers of our atmosphere. So, in this explainer, we're going to break down exactly how that works. All right, so let's start with the big central question for our explainer. We all know the tropics get hammered with direct sunlight pretty much all year long. So, why don't they just keep getting hotter and hotter until the oceans boil? And at the same time, why don't the poles, which get way less sun, just freeze solid? Well, the answer is this huge planet wide energy transfer system. To get our heads around this, the best way to start is to think of Earth's energy just like a financial budget. You've got energy coming in, that's your deposits, and you've got energy going out, your withdrawals. And for the planet to stay, livable, the books have to balance. Now, that main deposit, the energy coming in, it's got a name: insolation. It's basically a catch-all term for all the energy arriving from the sun, and it travels to us as short-wave radiation. That's a key term we're going to be using. And here is the single most important rule of this whole system. It has to stay in balance, in equilibrium. If 100% of energy comes into the system, then 100% has to eventually go back out. Earth can't just keep soaking up heat forever. So of that 100% of energy that's coming in, what happens to it? Well, here's the wild part. Right off the bat, almost half of it doesn't even make it to the party. This number, 49%, is absolutely crucial. And that reflected 49% has a name, too. It's called albedo. This is all the energy that gets bounced straight back into space by anything bright and reflective, like big white clouds or the snow and ice at the poles. It's basically like a giant planetary mirror. Okay, but here's where that simple budget idea gets way more complicated. This is where the planet's incredible balancing act really begins. Because while the total energy budget for the whole planet balances out, it is not balanced everywhere. I mean, not even close. And this image right here shows you the core problem perfectly. If you look between roughly 35 degrees north and south of the equator, there's an energy surplus. More energy is coming in than is going out. But if you look towards the poles from there, you see a massive energy deficit. Way more heat is being lost than is being gained. And you can see the hard numbers right here. I mean, just look at the difference. The poles are only getting about 70 watts of energy per square meter, but the subtropical deserts can get hit with over 320. That is a huge imbalance in the books. So this brings us right back to our big question. If the tropics are constantly gaining heat and the poles are constantly losing it, how does the planet stop itself from going completely out of whack? How does it balance its own books on a global scale? Well, the main answer is our atmosphere, and specifically the movement of air, what we call wind. You can think of wind as a global courier service, constantly picking up excess heat from the areas that have a surplus and delivering it to the areas that have a deficit. And it all kicks off with a super simple principle. When you heat up air, it expands. It becomes less dense, lighter, and it rises. And when that air moves up and away, it leaves behind an area of lower pressure down at the surface. So now you have a pressure difference. And if there's one thing nature always tries to do, it's seek balance. So air will naturally start to flow from an area of high pressure to an area of low pressure to even things out. And that horizontal movement, well, that's what we feel and call wind. It really is that simple at its core. But of course, it's never quite that simple, is it? The air doesn't just travel in a nice straight line from high to low. There are these invisible forces acting on it, basically steering its journey as it moves across the globe. So there are three main forces we need to wrap our heads around, and they all work together. We have the pressure gradient force, the Coriolis force, and the frictional force. Let's take a look at how they all interact. First up, we've got the PGF, or the pressure gradient force. You can think of this as the engine. It's that initial push that gets the air moving in the first place, from high to low pressure. And the bigger the pressure difference over a certain distance, so the steeper that gradient is, the faster the wind is going to blow. All right, now for the curveball. Literally, because our planet is spinning, any object moving over its surface, including a chunk of air, gets deflected from its path. This is the Coriolis force, and it's the reason big weather systems like hurricanes spin. The easiest way to remember Farrell's law for this is just to remember that in the northern hemisphere, the deflection is always to the right of the direction the wind is trying to go. So, north is right. And last but not least, we've got the brake pedal. friction. It's exactly what it sounds like. As wind blows over mountains, forests, even the surface of the ocean, the Earth itself creates drag, and that slows the whole process down. So all of these forces, you've got the initial push, the spin, and the drag, are all acting on the wind as it moves through this vast, vertically structured stage that we call our atmosphere. See, our atmosphere isn't just one big blob of air. It's neatly stacked in layers that are defined by their temperature. From the ground up, we have the troposphere, the stratosphere, the mesosphere, and way up high, the thermosphere, each with its own range of altitudes. Now, the really crucial layer for us, for everything we've talked about, is the troposphere. It's the bottom layer. It's where we live. This is where all the weather happens. The clouds, the rain, the wind, all of it. And critically, it's where temperature actually decreases the higher up you go. This slide really ties it all together. It shows how each layer's temperature profile is dictated by what's in it to absorb energy. Down here in the troposphere, it gets colder with height because it's heated from the ground up by radiation leaving the Earth. But then you hit the stratosphere and the temperature starts going up again because the ozone layer up there is amazing at absorbing incoming solar energy. And the pattern just keeps changing as you go higher, all depending on what gases are there to catch the sun's rays. So as we've seen, it's this incredible self-regulating system, a massive atmospheric engine driven by imbalance, steered by these invisible forces, all working together to keep the planet's books balanced. And that leaves us with one final, really critical question to think about. What happens to this incredibly delicate system when we start to tip the scales?